We like to say there's nothing there, as if that's the simplest state the universe can have. But the whole history of physics keeps saying the opposite. The closer we look at what we used to call empty space, the less it behaves like zero. Even in antiquity, it was not that simple. In the 5th century before Christ, Democritus split reality into two basic things: atoms and the void between them. Atoms were what exists. The void was where they move. He didn't give the void any forces, but he already made one crucial move. Without the void, motion is impossible, which means that even in the very first picture, nothing was a condition for something. 2,000 years later, Isaac Newton made that intuition rigid. By the late 17th century, as he was writing the mathematical principles of natural philosophy, the Principia, he treated space as absolute, the same for everyone, not depending on the observer, not changing because of what happens inside it. Bodies fall, planets orbit, tides rise and fall, but space itself does not take part. It is a stage. That version of emptiness was loved in science exactly because it was so economical. If you remove all bodies, the stage stays. If you bring them back, it accepts them. No hidden energies, no background pressure. The trouble started to show up in the 19th century when physicists began to describe the world not just with bodies, but with fields. Electric and magnetic phenomena, light and later gravity. Cast as a field, all of that needed a medium in which values can exist and change. The idea appeared: even if there are no particles in space, there is still a field there, only in its lowest possible state. In the 20th century, quantum field theory made that step irreversible. You cannot simply switch everything off. Even if you remove every real particle, the field remains, and it has a minimum energy. That was the first real hit to Newton's empty stage. At the same time, another question surfaced, the one Lawrence Krauss later made popular. What do we actually mean by nothing? Do we mean an absolute absence of being, or do we mean a physical state from which you cannot extract any more energy? Those are two different nothings. The first one belongs to metaphysics. The second one belongs to measurements. Physics works with the second one. It says if a state can produce fluctuations, even brief, even virtual, then it is already not empty in the everyday sense. Quantum mechanics added one more uncomfortable detail. The uncertainty principle says that a field at every point in space cannot be strictly zero in energy and strictly fixed in time. It must jitter a little. Those jitters cannot be turned off with a switch. They are fundamental, which means that even if we clean space from matter and light, processes would still be going on in it. It sounds like a paradox. Nothing is behaving as if it is something. In the 20th century, another line was added. Albert Einstein's general theory of relativity showed that space is not just a stage, but an object that can be curved, stretched, squeezed. If you put mass into a region, the geometry changes. If you remove the mass, the geometry can stay changed. Space became dynamic, and that means that even if we remove every body, we still have to ask, what kind of space is left? Flat? Curved? Expanding? That one question already shows that nothing in cosmology is not only about the absence of things. It gets worse. At the end of the 19th century, astronomers argued about Olber's paradox. If there are infinitely many stars and space is infinite, why is the night sky dark? In Newton's simple world, the sky should be flooded with starlight, but it isn't. Later cosmology will explain it as a consequence of the finite age of the universe and of the expansion of space. But what matters for us is the subtext. Even a nothing that looks like a dark sky is tied to dynamic properties of space. That is why the question, what is nothing in modern physics, is not rhetorical. On its answer depends how we explain the birth of the universe, what we call vacuum, and why space right now is expanding with acceleration. If vacuum is simply a state with zero energy, it must be passive. If vacuum is a state with the lowest possible energy, but not zero, then it can act. Then quantum fluctuations of the early universe could have come out of it. Then it can be the thing that is pushing galaxies apart right now. So the paradox is this: In everyday language, nothing is the absence of properties. In the physics of the 20th and 21st centuries, nothing is a state that has energy, has pressure, and can enter Einstein's equations. We keep calling it empty because there are no ordinary particles in it. But in essence, it is a special kind of something. And if we want to understand how everything matter, radiation, structure, could appear at all, we first have to admit the thing we casually called nothing was never really nothing. To understand nothing is to understand the starting state of space from which our universe could arise, and the quiet force that will keep steering it when matter and light no longer matter. We like to say there's nothing there, as if that's the simplest state the universe can have. But the whole history of physics keeps saying the opposite. The closer we look at what we used to call empty space, the less it behaves like zero. Even in antiquity, it was not that simple. In the 5th century before Christ, Democritus split reality into two basic things: atoms and the void between them. Atoms were what exists. The void was where they move. He didn't give the void any forces, but he already made one crucial move. Without the void, motion is impossible, which means that even in the very first picture, nothing was a condition for something. 2,000 years later, Isaac Newton made that intuition rigid. By the late 17th century, as he was writing the mathematical principles of natural philosophy, the Principia, he treated space as absolute, the same for everyone, not depending on the observer, not changing because of what happens inside it. Bodies fall, planets orbit, tides rise and fall, but space itself does not take part. It is a stage. That version of emptiness was loved in science, exactly because it was so economical. If you remove all bodies, the stage stays. If you bring them back, it accepts them. No hidden energies, no background pressure. The trouble started to show up in the 19th century, when physicists began to describe the world, not just with bodies, but with fields, electric and magnetic phenomena. Light and later gravity cast as a field. All of that needed a medium in which values can exist and change. The idea appeared, even if there are no particles in space, there is still a field there, only in its lowest possible state. In the 20th century, quantum field theory made that step irreversible. You cannot simply switch everything off. Even if you remove every real particle, the field remains, and it has a minimum energy. That was the first real hit to Newton's empty stage. At the same time, another question surfaced, the one Lawrence Krauss later made popular. What do we actually mean by nothing? Do we mean an absolute absence of being? Or do we mean a physical state from which you cannot extract any more energy? Quantum mechanics added one more uncomfortable detail. The uncertainty principle says that a field at every point in space cannot be strictly zero in energy and strictly fixed in time. It must jitter a little. Those jitters cannot be turned off with a switch. They are fundamental, which means that even if we clean space from matter and light, processes would still be going on in it. It sounds like a paradox. Nothing is behaving as if it is something. Space became dynamic, and that means that even if we remove everybody, we still have to ask, what kind of space is left? Flat? Curved? Expanding? It gets worse. At the end of the 19th century, astronomers argued about Olber's paradox. If there are infinitely many stars and space is infinite, why is the night sky dark? In Newton's simple world, the sky should be flooded with starlight, but it isn't. If vacuum is a state with the lowest possible energy but not zero, then it can act. Then quantum fluctuations of the early universe could have come out of it. Then it can be the thing that is pushing galaxies apart right now. So the paradox is this. In everyday language, nothing is the absence of properties. In the physics of the 20th and 21st centuries, nothing is a state that has energy, has pressure, and can enter Einstein's equations. We keep calling it empty because there are no ordinary particles in it, but in essence, it is a special kind of something. And if we want to understand how everything matter, radiation, structure could appear at all, we first have to admit the thing we casually called nothing was never really nothing. If emptiness were truly empty, it should not press. bend, or add energy to the equations that describe the universe's evolution. Nothing should not do anything, and yet by the end of the 20th century, identical signals began to emerge from completely different areas of physics. What we used to call vacuum behaves like a real physical medium. It interferes, it leaves traces, it influences the unfolding of the cosmos. In astrophysics, this became dramatically clear in 1998, when two independent teams, Saul Perlmutter's group at Berkeley and Brian Schmidt and Adam Rees's team, studied distant Type 1a supernovae and found something no one had predicted. The universe's expansion is accelerating. Even in regions almost devoid of stars or gas, where space seems perfectly empty, it keeps stretching outward. To describe this, physicists had to restore the cosmological constant to Einstein's field equations, the very same term he once called his greatest blunder. But now it stopped being a blunder. It became a clue. Even space that appears empty must carry energy. It behaves as though the vacuum itself has its own faint but uniform density, a subtle pressure pushing galaxies apart. In the laboratory, the picture turned out the same, only closer and more tangible. In the mid-20th century, experiments later known as the Casimir effect were performed. The setup was simple. Two extremely smooth, conductive plates were placed a few micrometers apart in a vacuum chamber. The air pumped out, everything stripped away to reach the closest thing to nothing. According to classical physics, the plates shouldn't attract each other, but they did. The explanation was unsettling. The space around the plates is filled with tiny quantum ripples of the electromagnetic field, and inside the narrow gap, some of those ripples simply cannot exist. There is slightly more pressure outside than inside, and the plates move together. Even empty space behaves as if it stores energy that can be redistributed. The experiment was a direct blow to Newton's picture of space as a passive stage. Atomic physics had noticed this much earlier. In 1947, Willis Lamb and Robert Rutherford measured the energy levels in the hydrogen atom and found a small but consistent shift, not predicted by existing theory. It became known as the Lamb shift. The cause: the electron is not orbiting in perfect emptiness. It is constantly interacting with a restless quantum vacuum, where virtual particles flicker in and out of existence. The background we assume to be zero adds a correction to the electron's energy, and that correction is always the same, no matter how often we measure it. If the vacuum were true, nothing, there would be nothing to interact with, and no shift at all. Put together, a strange and stubborn pattern emerges, on three independent scales: in the microworld of the atom, in laboratory experiments, and in the cosmic behavior of galaxies. The same motif repeats. Where we once said there is nothing, we find activity. The void creates a measurable force between metal plates. The void alters the structure of atomic energy levels. The void accelerates the expansion of the universe. It's not an experimental accident or a calibration glitch. It's the same signature, written across every scale of reality, from hydrogen to the cosmic web. And that leads to the central question of this whole investigation. If the thing we kept calling vacuum can actually do something, can we honestly keep calling it nothing? Either the vacuum is not empty at all. It is filled with zero-point energy, tiny quantum ripples, and a real vacuum pressure. Or our idea of nothing was just a household metaphor that never worked for the real universe. In both scenarios, the ground under our physics moves. Either emptiness has structure, or we've misunderstood the meaning of nothing all along. If the vacuum really does have its own energy, then modern cosmology of the 2000s and the 2020s hangs together. The framework we now call the Lambda cold dark matter model, that is, cosmological constant plus cold dark matter, explains three things at once: the accelerated expansion, the structure of the cosmic microwave background, and the way galaxy clusters grew over time. The logic inside it is very clean. About 5% is ordinary baryonic matter, about 25% is cold dark matter, and about 70% is that uniform pressure of the vacuum itself. Exactly this picture was backed in 2003 by the Wilkinson Microwave Anisotropy Probe, and then refined in 2013 and 2018 by Planck. To make the map of the cosmic microwave background match what we actually observe, the cosmological constant has to be there as a real physical component, not as a convenient knob. But if the vacuum is actually empty and carries no energy, if the acceleration we saw is just a calibration mistake on supernovae or a bad way of averaging an inhomogeneous universe, then not one paragraph in the textbook falls out. The foundation of the whole model does. The Lambda, cold dark matter model stands on the claim that there is an energy of empty space that does not change with time. Remove it, and now you must explain why the universe is expanding faster today than it was 10 billion years ago. You will have to change how gravity works on very large scales. Exactly what researchers tried to do in modified Newtonian dynamics, and in those modified gravity frameworks that replace the R term in Einstein's equation. You will have to rematch the large-scale structure with the microwave background. You will have to explain why Planck and the Wilkinson Microwave Anisotropy Probe produce the same acoustic peaks. In other words, the price of being wrong is not we mislabeled emptiness. The price is we have to rewrite the standard picture of the universe for the last 20 years. There is an even harder example. If you do not put the cosmological constant into the Friedmann equations, and assume the universe is filled only with matter and expands because of its early impulse, you get a younger universe. In that classical no-Lambda model, the age comes out to about 9 to 10 billion years. But astronomers already in the 1990s knew that globular clusters in our own galaxy were about 12 billion years old, or even older. That was absurd. Stars older than the universe itself. Introducing a non-zero cosmological constant raised the age estimate to about 13.8 billion years and brought stellar evolution back into agreement with cosmology. So the question, does the vacuum have energy, instantly becomes the question, did we miss the age of the universe by billions of years? This matters even more for the universe's future. If vacuum energy is real and truly behaves like a constant, which is what current Planck collaboration data favor, then as matter gets more and more diluted, that vacuum term will become the main actor. The expansion will accelerate. Galaxies will slide beyond the cosmological horizon, and every gravitationally bound system will be left alone in darkness. That is the late dark universe scenario. But if the vacuum is actually empty, and the acceleration was only an apparent effect, the future can be softer. The expansion slows down. Structure survives longer, and the cosmos does not break into isolated islands so quickly. We are not arguing about a word. We are arguing about which universe we are living in 100 billion years from now. That is why this is not a semantic debate. It is a debate about the structure of reality. If there is no vacuum with energy, then the standard model of cosmology, the very one where the distant supernovae observed in 1998, the microwave background measured in 2003 by the Wilkinson Microwave Anisotropy Probe, and the map taken in 2013 by Planck all line up, rests on a fiction. If it does exist, then we have for the first time seen pure emptiness steering the fate of galaxies. A mistake here costs us the age of the universe, its future, and every cosmological constant we currently call established. In the classical picture of the world, emptiness was always the stage, never the actor. It was the place where things happened, not the thing that made them happen. That is how space was imagined by the early natural philosophers and by the physicists of the early modern era. Atoms move in the void, planets travel through space, but the void itself does not do anything. It has no mass, no energy, no direction, no time arrow, it just exists. Isaac Newton made that picture strict. For him, space was absolute, uniform, motionless, the same for every observer. Inside it you can measure distances and times, describe motions, compute forces. Space does not resist and does not assist. It does not expand and does not shrink. Space is an ideal stage with no actors, no scenery, no sound. It does not change because something happens on it. If you place planets on the stage, they will move under gravity, but the stage will remain what it was. If you remove all planets, the stage will not vanish. It will stay simply empty. That picture turned out to be incredibly convenient. It allowed scientists to build accurate models of motion, track trajectories, find laws. The simplicity of space helped uncover the law of universal gravitation, and for a long time no one saw a reason to doubt that this was the right description of reality. There were no extra entities, no hidden layers, only bodies and the nothing between them. When physics switched to the language of fields, this view of emptiness almost did not change. New objects appeared: electric and magnetic fields, the gravitational field, and later quantum fields. But even then, there was still the option to turn everything off. If the field is equal to zero, if there are no particles and no excitations, then space is in the state of rest. That vacuum is called ideal vacuum. It carries no energy, creates no pressure, and does not influence the system. In that state, the minimum value of the field is zero, and the energy of the system is also zero. That is the classical definition of emptiness. The field is at its minimum. The energy is zero. This idealized vacuum became the reference level for calculations. In particle physics, it is the baseline, the zero line from which every deviation is measured. If an excitation appears in the field, we can treat it as a particle. If there are no excitations, the system is in the vacuum. On this idea, the whole building of quantum field theory was erected. Even the word particle there literally means a thing that exists against the background of the ideal vacuum. Without that background, the word particle has no clear meaning. This description looks elegant. It lets us calculate, predict, and test. It has a clean logic: remove everything, and nothing remains. Mathematically, it is beautiful. Zero in the equation is not just nothing. It is a stable state where everything is balanced. Space does not need to be fed energy. It does not generate itself. It does not interact with what is not in it. It is completely neutral. This approach also works at the level of intuition. It gives a sense of stability. The world can be complicated, but its base layer is simple. Under all forces, interactions, and objects, there is a basic level, a clean background that does not interfere. It is as if physics had finally found a point of leverage, a zero on which everything else can be built. If something is happening somewhere, it is because something appeared there, not because space itself got involved. Classical emptiness is also attractive, philosophically. It allows you to separate being and non-being. There are things, stars, planets, particles, and there is non-being, the empty space between them. That separation feels natural. It removes the anxiety of the unknown. You can describe the world as a set of things, and everything else is just intervals. No hidden variables, no spirits of space, only what can be seen or calculated. In particle physics, this ideal shows up right inside the equations. When we write that the field is zero and the energy is zero, it is not a metaphor. It is a literal definition. The minimum value of the field is zero. The minimum energy is zero. Space does not store reserves. It does not stockpile hidden force. It exists as a geometric arena that does not affect events. If you draw a boundary between two regions of that space, both sides of that boundary are identical. No difference in density, temperature, or pressure. Perfect symmetry. The main arguments for this picture are simplicity and predictability. The system of equations is tame. There are no hidden parameters. There are no spontaneous jitters. Every change can be traced back to an external cause. Space cannot act on its own, which means all dynamics belongs to matter and to the forces that bind it. That is convenient. That gives control. That turns physics into a strict science of interactions, not of mysterious entities. There is one more reason the classical vacuum looks so obvious. It agrees with the basic conservation principle. If energy cannot appear from nowhere, then empty space should not have any. Zero produces zero. For energy to appear, you must introduce a cause, a collision, radiation, motion. Without that, space stays a blank page. You can write on it, but the page itself says nothing. With this kind of vacuum, we could build a huge number of working models. From simple ballistics to celestial mechanics, all you needed to know were forces and masses. The emptiness did not participate, it simply was there. Even when Albert Einstein created the general theory of relativity and allowed space to curve in the presence of matter, the old intuition still survived. If you remove everything, there is a limit in which geometry becomes flat and neutral again. The seed of the idea, if we take everything away we get zero, stayed with us. In this logic, a vacuum with zero energy is not just a handy abstraction. It is the most natural base of the world. It is clear, it is transparent. It does not demand more explanation. If energy appears somewhere, it must have come from somewhere. If it disappears, it must have gone somewhere. Everything obeys balance. So the official, classical version of nothing sounds like this. The world has space, but that space has no energy of its own. It cannot act. It does not create effects. It serves as a stage for matter and radiation, but it does not become a character. It is background, not protagonist. But what if that simplicity was only an illusion? The trouble with the classical picture of emptiness is that it did not break in theory. It broke in experiment. We wanted the vacuum to be a state with zero energy, a stage with no actors, but the instruments kept saying the same thing. The stage is playing. In places where we expected a clean zero, forces appeared, energy levels shifted, and on cosmic scales, space itself began to accelerate. Emptiness refused to stay empty. One of the clearest pieces of evidence is what we now call the Casimir experiment. On paper, it is almost childish. Take two very smooth, highly conductive metal plates, place them in a vacuum, and set them a tiny distance apart. No air between them, no molecules between them. By classical logic, nothing between them. And yet when the experiment was performed, the plates started to move toward each other. Not because they were magnetized, not because they were tied together, not because a current was applied. They moved because the space between the plates turned out to be different from the space outside them. Outside, the quantum activity of the electromagnetic field, those tiny quantum ripples, is full. Inside the narrow gap, some of those ripples cannot exist. The pressure outside is ever so slightly higher than the pressure inside, and the plates are pushed together. The vacuum created a pressure difference. The thing we called nothing behaved like something. A very similar story showed up in atomic physics when physicists began to measure the energy levels of the hydrogen atom. With extreme precision, quantum mechanics gave clear, neat values for those levels. But when the spectrum was measured on high-sensitivity setups, the lines were just a little bit off. That shift could not be explained only by the interaction between the electron and the proton. Physicists had to admit, the electron is not moving in a perfectly empty space. It is surrounded by a seething quantum vacuum that on very short timescales creates and destroys virtual particles. The electron feels that foam and its energy changes because of it. This effect was named the Lambda shift, and in essence it says one thing. Even in the simplest atom, the vacuum is not equal to zero. It adds a correction. If it were only laboratory effects, we could have waved it away. That's just an instrument quirk. That's just delicate quantum math. It will not show up on large scales. But on the largest scales we found the same pattern. When astronomers measured the recession speeds of distant galaxies and compared them with what gravity predicts, they found that the universe is not only expanding, it is doing it with acceleration, as if something is adding energy straight into the fabric of space. This extra term was described as the cosmological constant. Physically, it is most often interpreted as vacuum energy that fills space uniformly. Even where there is not a single galaxy, not a single photon, this energy is still there and still working, which means the vacuum is acting not as an absence, but as the most stable and most widespread component of the cosmos. In all three cases, in the Casimir experiment, in the Lambda shift, and in the accelerated expansion, we run into the same motif. We try to set emptiness, and it answers with action. We say, this is zero, and the instrument says, there is something here. We calculate the energy as zero, and the measurement gives us a small but non-zero number. Emptiness refuses our definition. It behaves as if it has structure. This is especially clear if we recall the classical verbal definition of vacuum as the state of minimal energy of the field. We said the field is at its minimum. The energy is zero. But if a force appears between plates, then some modes of the field were cut out. If a shift appears in the atom, then the electron is interacting with something. If space is accelerating itself, then there is a non-zero energy density in the gravity equations, even for the empty state, which means the minimum energy is not true absence. It is the lowest active state, not nothing, but as little as nature allows. Against this background, the classical version A starts to crack. Its two main virtues, simplicity and predictability, turn out to be the price we paid for not describing real measurements. Simplicity says, emptiness does not act. Experiment says, it does. Simplicity says, if you remove everything, you get zero. Experiment says, if you remove everything, you still get a tiny measurable remainder. Simplicity says, the stage does not affect the play. Experiment says, the stage is pushing the actors and stretching the hall. You can try to write it off as systematics. You can say, the plates were not perfectly parallel, so they moved. You can say, there were unaccounted for effects in the atomic spectrum. You can say, the supernova sample was biased. But three independent manifestations of the same idea, that the vacuum leaves a trace, is no longer random noise. It is a repeating signature. It is the vacuum refusing to be just background. We thought we had described emptiness once and for all, a clean zero that could sit at the bottom of every equation. We used it as the baseline for our calculations, and even for our textbooks. But when the instruments became sensitive enough to see very small energies and very delicate effects, reality answered differently. The classical zero was not the real one. The nothing we trusted was behaving like something. Nothing is behaving as if it was never nothing. Maybe we have been misreading the void this whole time. Right after results started to accumulate that seemed to show an active vacuum, some physicists and astronomers took a deliberately cautious position. They said, before we declare empty space a new form of matter and add it to the list of things that drive cosmic dynamics, we have to check everything that can be checked. Any tiny effect can turn out not to be a property of the universe, but a feature of the measurement, especially when we are talking about extremely small quantities and about instruments working at the edge of their sensitivity. So the first line of defense was, we are not seeing the vacuum act. We are seeing complicated noise. In laboratory experiments, this explanation looked plausible. The Casimir experiment requires almost perfect geometry. The plates have to be strictly parallel, the surface has to be very smooth, and the distance has to be extremely small. Even a slight tilt creates attraction. Even a thin contamination on the edge creates attraction. Even a residual electric charge on one plate creates attraction. So it was reasonable to say there is no vacuum pressure here. We just did not make the experiment ideal. What looks like the action of the quantum vacuum is in fact the combined effect of geometric imperfections and leftover fields. A similar criticism was aimed at precise spectral measurements. The Lambda shift is a tiny quantity. To see it, you have to remove a whole set of side factors, magnetic fields, temperature drifts, frequency calibration errors. The skeptical version sounded like this. We are attributing to the vacuum what is actually caused by the non-ideality of our setup. We are measuring not zero plus a vacuum correction, but zero plus all our lab imperfections. In that sense, skeptics would say that the void does not act. Only our instruments do. Sounded perfectly rational. If we are working at the level of billionths of energy, we must first rule out every way to spoil the experiment, and only then talk about fundamental properties of emptiness. In cosmology, this caution looked even more justified. Distant Type 1a supernovae were used as standard candles to measure how fast galaxies are moving away. But these objects are at enormous distances. Their light passes through dust, through gas, through large-scale structure. It was reasonable to assume that part of the brightness was simply lost on the way, and we read that loss as an accelerated expansion. It was also reasonable to assume that we selected only those supernovae that were easy to see, and those that would have given a different value simply did not enter the sample. In that case, the acceleration effect is not the action of the vacuum, but the result of selective data picking. Another line of skepticism appeared: a geometry error. All the calculations with redshifts and brightness curves were done under the assumption that space is on average homogeneous and isotropic, that is, the same in every direction. But what if it is not? What if we live inside a large underdense region, and outside it, the density is different? Then the light from distant objects will behave differently than in a perfectly homogeneous universe, and part of the observed acceleration can be explained by the fact that we misread the global shape of space. In that case, no vacuum is needed. Geometry alone can do it. On this background, an idea of a false vacuum also appeared in a practical, observational sense. We are not measuring the absolute energy of empty space. We are measuring a local disturbance around instruments, around massive bodies, around the walls of the experiment. Near conducting surfaces, the spectrum of quantum ripples really changes. So what we are seeing is not a property of the global vacuum of the whole universe, but a property of a specific configuration, where there are no plates, no walls, and no bounding surfaces. The vacuum may really be empty, and we mistakenly took a local effect for a universal one. Skeptics also reminded everyone that calculations of vacuum energy in quantum field theory give an absurdly large value, bigger than the observed value, by about 120 orders of magnitude. If the vacuum behaved exactly the way naive quantum calculations say, the universe would have blown apart instantly, but it did not. That meant that either the theory gives a huge background zero that is somehow subtracted, or the vacuum energy we observe is not a fundamental constant at all, but a small leftover and basically accidental value. Then one could say, we just happen to live in an era when this leftover is not equal to zero. This is not the action of the void. This is the peculiarity of our time slice. There were subtler versions too. For example, that gravity itself, as the geometry of space, is sensitive to large-scale inhomogeneities and can imitate an acceleration effect, or that we still do not fully understand how to average matter density over very large volumes. And because of that, an extra term appears in the equations, which we habitually call the cosmological constant. In such an approach, the vacuum has no energy of its own. We just picked the wrong formula for the average. In all these variants, one skeptical point stayed the same. The void does not act. Our instruments, our methods, and our assumed geometry act. We are not seeing a new property of reality. We are seeing the reflection of how we measure it. It was an attempt to preserve the classical simple version of emptiness, because the simple emptiness is elegant. It is easy to understand, and it does not force us to introduce a mysterious energy of nothing. But as the precision of observations grew and the data set widened, the signals refused to go away. The Casimir effect was reproduced again and again, on different setups. The Lambda shift was confirmed in different conditions and for different atomic systems. The cosmological acceleration was recovered not only from supernovae, but also from the cosmic microwave background and from the large-scale distribution of galaxies. The source was the same, and the methods were different. The data would not disappear. The doubts lasted for a long time. It looked as if, with just a bit more careful checking, the whole story about vacuum energy would turn out to be a beautiful misunderstanding, a lucky overlap of measurement errors. But the universe did not let the signal go. The more new measurements appeared, the harder it became to dismiss them as noise. The effect kept showing up again and again, with different instruments, different methods, and on different scales. Type 1a supernovae were the first serious blow to the skeptics. These explosions are used as standard cosmic candles. Their peak brightness is so stable that it lets us measure distances with percent-level accuracy. When two independent groups, the Supernova Cosmology Project and the High-Z Supernova Search Team, compared the brightness of very distant explosions with the brightness they expected, they both saw the same thing. Galaxies are receding faster than they should, and they were doing it in every direction. The selection bias was checked first. The supernovae were evenly distributed. The dust correction was checked. The spectra were corrected by wavelength. Even the telescope calibrations were cross-checked between the teams. And the result was still the same: the acceleration is there. When these data were first shown at conferences, many people decided the effect could be explained by a local inhomogeneity, as if our region of the universe was just slightly emptier than average. But new observations quickly broke that explanation. The measurements came from the southern and northern hemispheres, from ground-based telescopes and from orbital observatories. In every patch of the sky, the result was the same. If the acceleration were an illusion of geometry, different directions would have given different values. They did not. Then came the cosmic microwave background, the oldest light in the universe, carrying the imprint of the first 400,000 years of space. The COBE satellite, then the Wilkinson Microwave Anisotropy Probe, and finally Planck drew a map of that radiation, with accuracy down to millionths. On that map there were tiny temperature variations corresponding to early waves of density. Their shape matched exactly what you get when a cosmological constant is present. Without vacuum energy, the structure of the microwave background would have looked different. The radiation confirmed not only that the acceleration exists, but also the actual value of the energy density. It was the same number as in the supernova data, only now it was coming from a completely different epoch, when the universe was less than 1 million years old. A third confirmation came from gravitational lensing. Massive clusters of galaxies bend space, and light from even more distant objects curves around them like through a lens. From the amount of distortion, astronomers can tell how the mass is distributed and how the geometry of space is changing with time. When thousands of such lenses were analyzed, the same accelerated trend appeared. Space is not just expanding, it is speeding up. And the speed up shows itself the same way when you look at matter, at light, and at geometry. To rule out systematics, the projects checked one another. Supernovae were measured with the Hubble Space Telescope, and with Subaru, in visible light, and in the infrared. The microwave background was recorded by antennas on different orbits, with different detectors. The lensing data were collected by ground observatories, and by space missions such as Euclid and the Hubble Frontier Fields program. There were no shared instruments between all of them. Statistical independence was built in, but in the equations the same quantity kept appearing every time. Later, new methods were added: baryon acoustic oscillations, the frozen sound waves of the early plasma. They show up in the distribution of galaxies as a barely visible ripple and let us measure the scale of space in different eras. Those oscillations gave the same cosmological constant. Then came data from polarization of the microwave background. Again, the same value. More and more independent experiments, fewer and fewer doubts. Even when skeptics proposed to reprocess all the data blind, with the brightness and distance values hidden from the analysts, the result did not change. The teams recovered almost identical parameters. That was the decisive moment. In physics, nothing is more persuasive than the coincidence of numbers obtained by different people, with different instruments, using different methods. Step by step, the argument about imperfect instruments began to sound outdated. The instruments changed, generation after generation. The effect stayed. The geometry error disappeared once isotropy was confirmed. The acceleration is the same in every direction of the sky. The selection error disappeared once the number of supernovae passed 1,000. The dust error disappeared once the spectra were corrected for absorption at all wavelengths. Noise cannot stay the same everywhere, and systematics cannot copy itself on 3 independent scales. The scientific consensus was formed not out of belief, but out of stubborn data. Every new observation that was supposed to break the picture only made it stronger. Laboratory effects, astronomical measurements, relic radiation, they all showed the same thing. And if three independent instruments see the same number, then that number belongs to the universe, not to the laboratory. Over time, new cross-checks were added. Background neutrinos, relic gravitational noise, the structure of galaxy clusters. Everywhere the same fraction of vacuum energy density appeared, about 70% of the total. That value passed through epochs like a mark, left by nature itself. At that point, scientists stopped talking about systematics and started talking about new physics. Doubt turned into acceptance. It became clear that the vacuum is not just a stage, but an active presence. It behaves like a uniform field that fills all of space, the same in every point and at every moment in time. This energy cannot be switched off, because it is built into the fabric of the cosmos. The universe kept repeating the same whisper. The same number was hiding in light curves, in microwave maps, and in lensed galaxy images. No matter which path the researchers took, the result was always the same. The void is not void. The story of the vacuum became serious, not when physicists said, maybe empty space has energy, but when a number appeared, a concrete repeating number. In the late 1990s, two independent teams, the team of Saul Perlmutter at Berkeley and the group of Brian Schmidt with Adam Rees, published results on distant Type 1a supernovae. That was in 1998. They measured the brightness of faraway explosions, compared it with the expected brightness, and suddenly got this: the universe is expanding with acceleration. To describe that, they had to introduce an energy that is uniform throughout space. When their cosmological parameters are converted into usual units, the result is a tiny value, about 1 × 10⁻⁹ joules in 1 cubic meter. 5 years later, in 2003, the space mission Wilkinson Microwave Anisotropy Probe produced a map of the cosmic microwave background. That is, light from the time when the universe was about 400,000 years old. A completely different epoch, a different instrument, a different method. But when astronomers matched the anisotropy spectrum to the models, a component appeared again that looked like vacuum energy, and its density was in the same order as for the supernovae. Not 10⁻⁻3, not 10⁻⁻15. Again, about 10⁻⁻9 joules per cubic meter. Which means the cosmos as we see it now, and the cosmos as it was a child, are telling us the same number. In 2013 and in 2018, the Planck mission photographed the same sky with even better precision. It had better angular resolution, better calibration, better removal of foreground signals from our galaxy, and Planck confirmed what came before, for the peaks and dips in the microwave background spectrum to be exactly where we observe them. The equations must contain a cosmological constant with an energy density of the order of 1 × 10⁻⁹ joules per cubic meter. 3 different datasets, the supernovae observed in 1998, the microwave background measured in 2003 by the Wilkinson Microwave Anisotropy Probe, and the improved map taken in 2013 by Planck, and in each of them the universe leaves the same signature. That was not all. In cosmology there is a third independent clock, baryon acoustic oscillations. This is the imprint of sound waves in the early plasma, frozen in as a faint ripple in the distribution of galaxies. When, in the 2010s, large sky surveys like the Sloan Digital Sky Survey and its successors started to measure that ripple, they too arrived at the same value of vacuum energy. Again, a uniform component. Again, very small. Again, exactly the one needed to explain acceleration. In another era, on other scales, using other physics, the same trace that already looked not like a systematic error, but like a fingerprint. Here, microscopic physics enters the frame. Back in 1947, Willis Lamb and Robert Rutherford measured in hydrogen a tiny shift of the energy levels, what was later called the Lamb shift. Later it was explained as the interaction of the electron with the fluctuating vacuum. The electron is swimming in a foam of virtual particles, and because of that, slightly changes its energy. That was the first practical signal that the vacuum is not zero. When decades later, these quantum corrections were expressed in terms of energy densities, it became clear, even here the vacuum leaves a trace of the same nature, it is not empty. On the other side stood theory. Quantum field theory, if you calculate it all the way, gives a colossal vacuum energy, about 10 to the power 90 joules per cubic meter. This gap between the observed value and the theoretical one was called the cosmological constant problem. Steven Weinberg wrote about it very clearly in the late 1990s. For the first time, we are seeing a value that nature has chosen, but we do not know why it chose something so absurdly small. Theory shouts, the vacuum should be unbearably heavy. Observation whispers, the vacuum is light, but not zero. Between the shouts and the whispers, there are 120 orders of magnitude. This is the key clue. We can argue about geometry, about dust, about the selection of supernovae. We can adjust parameters in the equations. But if three independent cosmic measurements, made in different years, by different teams, and on different instruments, give the same number in quantum effects and atoms point in the same direction, then this number is not our artifact. It is a property of reality itself. This is the constant of the void. It is small, but it is everywhere. It describes equally well the universe at the age of 400,000 years and the universe at the age of about 13.8 billion years. It enters the light curves of distant explosions and the map of ancient light in exactly the same way. It behaves as if the void itself has a fixed signature. The real strangeness is not that nothing has energy. The real strangeness is that nothing has energy at precisely this scale. A bit more, and galaxies would never have formed. A bit less, and the acceleration would not be visible. We live in an era when the void acts gently, but inevitably. Nothing has a constant signature, and it is frighteningly small. At first, it seemed that the universe's acceleration rested on a single kind of observation. Type 1a supernovae were bright cosmic beacons, but also an easy target for doubt. All it took was to say that they looked dimmer not because of distance, but because of dust, and the entire idea of an active vacuum would collapse. So the next step was obvious, to check whether the same acceleration could be seen through other eyes, with other instruments, using entirely different methods. If even one independent test had shown a different result, the hypothesis of Nenzai vacuum energy would have died. It did not die. First, researchers compared the late universe to the early one. Redshifts of galaxies recorded how space expands today. Meanwhile, the cosmic microwave background maps from the Wilkinson Microwave Anisotropy Probe and Planck showed the cosmos as it was 400,000 years after the beginning. Two different times, two different tools, two different teams, yet both datasets fit into the same Lambda cold dark matter model, demanding the same thing, a uniform vacuum energy filling space. Old light and new light pointed to the same cause. Then they looked at how galaxies are distributed. In the Sloan Digital Sky Survey, the Baryon Oscillation Spectroscopic Survey, and extended BOSS, millions of spectra helped reconstruct the rate of expansion across cosmic eras. The curve came out not linear, but accelerated. Baryon, acoustic oscillations, the standard ruler spanning tens of megaparsecs, produced the same pattern. It did not matter whether they measured through supernovae, through spectra, or through galaxy clustering. The universe behaved as if pushed by an invisible pressure. Gravitational lensing confirmed the same result. Light rays bent around massive clusters in a way that did not fit a universe without vacuum energy. Images of distant galaxies stretched and multiplied, and the time delays between quasar copies matched the geometry of accelerated expansion. Light, matter, and the very fabric of space told one coherent story. Next came the question, how big an error would it take to remove the effect? The answer, too large. For acceleration to vanish, the supernova brightnesses would all have to be systematically miscalibrated. Spectroscopy would have to misjudge distances, and lensing masses would have to be wrong, all in the same direction. Random noise cannot conspire like that. Noise scatters. This pattern aligned, always toward a quasi-vacuum. To rule out instrument bias, scientists compared the microwave background maps from different frequencies and from both missions, the Wilkinson Probe and Planck, and the results matched. Supernovae were observed through different telescopes and filters. The acceleration stayed. Gravitational lenses were analyzed with independent algorithms. The effect remained. The more the methods changed, the more stable the outcome became. Another test followed. Using baryon acoustic oscillations, astronomers measured the scale of structure in the nearby and distant universe. If acceleration were just an illusion, that cosmic ruler would have shown different distances. But the data again fell into the Lambda cold dark matter model. With the same share of vacuum energy, even the microwave background light formed hundreds of thousands of years after the beginning, and the galaxy distribution, billions of years later, both yielded the same number. In the early 2000s, papers still said cautiously, the observed acceleration may be a statistical artifact. By the middle of the decade, the phrasing had changed. The acceleration is confirmed by independent methods. And by the Planck era, in 2013, it was clear to erase the effect. One would have to discard entire classes of observations at once. Even then, the numbers would not line up. Each check turned skepticism into evidence. We wanted to prove we were seeing an illusion and found a pattern. We tried to remove the effect and found its copies across every scale. The universe repeated the same equation too consistently to be coincidence. If the acceleration were a statistical mistake, it would have vanished under cross-checking. But it stayed through supernovae, through the microwave background, through gravitational lensing. And that is when it became clear, nothing is not just empty. It holds a property that has survived every test, every refutation, every replacement of instruments. We searched for an error in the tools and found a constant of space. We tested the hypothesis to break it and proved the opposite. Nothing passed the test, simply by existing. It all began from a simple assumption. If we remove everything that can be removed, space should become neutral. Pump out the air, take away the heat. Subtract stars, gas, and radiation from the equations. Push the universe to the limit of emptiness. It looked like at that level physics should go silent. But the opposite happened. The more we cleaned space, the more clearly something showed up that was not supposed to show up. Plates in a good vacuum still attracted each other. Energy levels in the hydrogen atom still shifted. A cosmos with a minimal amount of matter still expanded with acceleration. The void behaved like something that cannot be erased. From this came the working conclusion. The vacuum is not an absence. It is a form of presence. It is a state that has parameters even when it has no particles and no light. In the microscopic world, it shows up as a continuous quantum foam. Fields cannot freeze exactly at zero. So in every point, virtual pairs flash into existence and disappear again. That gives the zero-point energy minimal, but not zero. In the laboratory, the same state pushes conducting plates toward each other. In cosmology, it appears as the fact that even empty regions of space keep swelling. The same handwriting on three different scales. The story with the cosmological constant made this especially sharp. Albert Einstein once put it into the equations of general relativity as an artificial term to get a static universe. Later, he called it his greatest mistake. But at the end of the 20th century, when supernova observations and then the map of the microwave background demanded a uniform source of energy, exactly that extra term came back and became central. It turned out that the mistake was not that the equations contained the energy of empty space. The mistake was that we did not understand its physical meaning. Nothing turned out to be something that really enters Einstein's equations. In the language of quantum field theory, it looks like this. You cannot make the energy of a field strictly equal to zero without breaking the uncertainty principle. The minimal state still fluctuates. That means the vacuum is active, by definition. It can create pairs. It can modify energy levels. It can change pressure. That is why it cannot be switched off. If we could switch it off, the Lambda shift would disappear. If we could switch it off, the Casimir effect would not appear. If we could switch it off, the redshift curves would not require a uniform energy. But all of these things are there, which means the vacuum is working all the time. On large scales, this activity looks very modest. The vacuum energy density derived from Planck data and from supernova observations is about 1 × 10⁻⁹ joules per 1 cubic meter. This is a frighteningly small value, but exactly because it is spread through all of space and does not get diluted as the universe expands, it starts to dominate with time. Matter thins out, radiation reddens, but this energy stays the same. That is how nothing takes over the fate of space. From this follows a new meaning of the word nothing. In everyday language, it is an absence. In the physics of the early 21st century, it is a minimal, but truly acting state. It does not look like matter, but it gravitates. It does not look like a field set by a source, but it gives pressure. It does not look like radiation, but it determines the evolution. We do not see it directly. It has no spectrum, no line in the telescope, but if we remove it from the equations, the curves, the maps, and the age of the universe stop matching. We cannot see it, but we cannot turn it off either. We can make space cold, rarefied, and dark, but we cannot make it less active than the active vacuum. That is the verdict. The void is an actor. Nothing does not disappear under checking. It stays. If the vacuum is acting, the next step is obvious. We have to find out whether it always acts the same way. Everything we see right now, the supernovae observed in 1998, the map of the cosmic microwave background from the Wilkinson Microwave Anisotropy Probe, and from Planck, the large galaxy redshift surveys, is described by one and the same picture. The vacuum behaves like a constant. But for now, that is an assumption. We accepted that its density does not change with time, because that makes the equations simpler and because the data fit better that way. Now the task is to check whether simplicity is fooling us. That is exactly why Euclid was launched, the European Space Telescope that is making deep and very wide surveys of the sky. Its goal is to build a map of weak lensing, the weak gravitational lensing, the barely noticeable distortions in the shapes of millions of galaxies caused by the distributed mass along the line of sight. If the vacuum is completely constant, that map should give one clear evolutionary track for structure growth. But if the pressure of empty space has changed even slightly, large-scale structures would have grown differently, and this will be visible precisely in weak lensing, because weak lensing is sensitive to all the mass along the path, not only to bright objects. After it, the same problem will be tackled by the Nancy Grace Roman Space Telescope, the American NASA Space Telescope. It will collect huge samples of distant supernovae, and at the same time will image sky patches at high resolution for gravitational lensing. So it will be able to look both at the standard candles and at the geometry of space at once. That double method is needed, not just to say the acceleration exists, but to say the acceleration in 2030 is the same as in 2005, or it departs slightly from the Lambda cold dark matter model. If it departs, then the vacuum may be evolving. In parallel, ground-based projects are building ever more precise redshift surveys, three-dimensional maps of galaxy distributions. In them we can extract the spectrum of dark energy, how strongly it affects expansion at different redshifts. If at some epoch the best fit comes with a parameter different from one, that will be a hint of dynamical dark energy whose density changes instead of staying fixed. Here the question becomes bold. We are used to thinking that nothing is a background that does not change. But if the coming data from Euclid and Roman show that the pressure of the vacuum in the early universe was even a little different, we will have to admit the void also has a history. Sometimes the loudest thing in cosmology is not a supernova burst and not the map of the cosmic microwave background. It is the silence in which nothing is supposed to happen, and yet something keeps happening. We removed the stars, we removed the gas, we went beyond clusters, beyond spirals, beyond dust, and there, where we expected a clean zero, we found activity. The Wilkinson Microwave Anisotropy Probe saw it in the ancient light. Planck saw it in the same ancient light, only measured more precisely. The supernovae observed in 1998 saw it in distant galaxies. Laboratory plates saw it in a gap of just a few micrometers. Everywhere we checked, the void left a signature. What we call nothing may be everything that holds the universe together. Maybe it is exactly this very small energy spread across an uncountable number of cubic meters that keeps the cosmos from collapsing. Maybe it is exactly what we used to call absence that is the common level on which space, time, and fields can exist at all. Maybe nothing is simply the state from which everything else can actually be made. Perhaps the void was never empty, only waiting to be understood.